Welcome. Today we are discussing Module 1.1, the anatomy of autonomous agents and the ReAct pattern theory. Here is a quick look at where we are in our curriculum. Hello everyone, and welcome to our series on autonomous systems. Today, we are stripping away the AI hype and looking under the hood of modern AI agent architectures. Standard LLMs are brilliant pattern recognizers, but they are fundamentally stateless and passive. By the end of this lecture, you will understand how we construct stateful, goal-oriented systems using the ReAct pattern. If you want to download our architecture diagrams and slides, make sure to check the link in the description below. To build an agent, we must provide it with a cognitive framework. The planning component decomposes complex goals into manageable steps. Memory ensures context isn't lost mid-flight, utilizing both short-term context windows and long-term vector database stores. Finally, tools allow the agent to affect the outside world, turning a closed LLM into a powerful interface for databases, web browsers, and local code environments. Here lies our core engineering problem. If you ask a raw LLM to book a flight, calculate tax, and update your database, it will likely hallucinate a successful response without actually executing anything. It lacks grounding. We must force the model to pause, observe its environment, and reason before moving to the next task. This is where classical software engineering meets generative models. The ReAct pattern introduces a powerful three-step sequence: thought, action, and observation. In the thought phase, the LLM reasons about its current state and goals. In the action phase, it selects a tool and outputs its parameters. Finally, in the observation phase, the runtime executes the tool and injects the output back into the LLM context. This loop continues until the final answer is reached. Let's translate theory into engineering. Here is a production-grade Python structural skeleton demonstrating the orchestrator engine. Note how we handle the parsing of thoughts and action tags, catch exceptions gracefully, and safely pass the tool responses back to the LLM context pool. Remember to check the link in the description to download this codebase and the full execution sequence diagram. As you can see on the terminal screen, our agent is presented with a query to fetch item details. Instead of blindly guessing, the LLM first creates a thought process to call the search API. Once the orchestrator executes the tool and injects the observation, in stock, the LLM reads the state and returns the definitive response. This structured flow eliminates hallucinated data vectors completely. To build resilient systems, we can't rely solely on basic prompt concatenation. As the agent's actions scale, the context window grows rapidly, increasing latency and operational costs. We mitigate this by building selective memory systems, sliding window history buffers, summary-based memory stores, and semantic lookup databases that retrieve relevant historical decisions precisely when needed. As professional system architects, we must anticipate failure modes. When an external tool returns an error, some agents will panic, retry indefinitely, and burn hundreds of dollars in API credits within minutes. To prevent this, we introduce hard stop limits on loops, validate tool schemas, and cache LLM responses to keep systems secure, deterministic, and cost-effective. We've built a solid conceptual foundation today. Now, it's time to build this ourselves. In our next lecture, Module 1.2, Building a Basic Reasoning and Acting, ReAct, Loop in Python, Practical, I will guide you step by step through writing a fully functional ReAct runner from scratch, completely independent of external agent frameworks. Make sure to download the slides and architecture diagrams using the link in the description, subscribe so you don't miss the upcoming session, and I will see you in the practical class.